Hello dear students, I am Meghamala, Assistant Professor from EC Department, Institute of Aeronautical Engineering. And today I am going to talk about, or else I am going to share something about the synthesis of synchronous sequential machines. So, in the previous classes already we have discussed about the sequential machines, analysis of sequential machines, and now coming to the synthesis of sequential machines. So what is the synthesis of sequential machines? Basically sequential machines are consist of the memory elements, right? So now we will see the procedure of, or else we will see the logic synthesis of how the sequential machines can be considered. So the procedural assignment is the assignment of a logic value to a variable within an initial or always statement. So as we are discussing the different statements in the Verilog VHDL, we have discussed about the procedural assignment statements. So the procedural assignment statements consist of blocking and non-blocking statements as well. So here, in order to write, or else if you are writing your code in terms of procedural assignments, then you have to remember that your code should contain the always statements. Okay, within or initial, within an initial or always statements. The procedural statement should contains in between the initial or always statement. And then this is the contrast to continuous assignment within the data flow modeling. So we have different types of assignment statements, procedural and the continuous assignment statement. So the continuous assignment statement consists of, it is a bit opposite to the procedural assignment statement. So what are we saying? That procedural assignment statement consists of the statement, the declaration of the input and output, and also the mechanism that you are following should be in between the initial or always at the rate statement. Okay, but whereas the continuous assignment statement doesn't need that. So this is a bit opposite to each other. And then the finite state machines. Coming to the finite state machines, because we have to concentrate on FSM, because the synthesis should be done with the synthesis will be done with respect to the FSM, finite state machines. So these FSMs, finite state machines, are significant for understanding the decision making logic as well as control the digital systems. So here, these machines, finite state machines, will make us to decide properly. So that we are telling that these are very significant machines. Okay, these are very prominent machines for decision making logic. Okay, for decision making logic, and as well to control the digital systems. In order to control the digital system and to make a wise decision of regarding the input and as well as the output, we are going with respect to the finite state machines. And then in the FSM, the output as well as the next state are present and the input function. So this finite state machine, it consists of the outputs as well as the next states, are present states, and the input functions. So it consists of four things: input functions, output functions, present state, and as well as the next state. Present state, next state, input, and output. So this finite state machine consists of all these things, and which means that the selection of next state mainly depends upon the input value and strength lead to more compound system performance. So here we have to concentrate something that the next state, or obviously the next state is observed only just because with the help of the present state. So the selection of next state, the selection of next state depends upon the input value, the present state of the input value, and strength that is leading to the more compound system performance. So the strength which is present at the present state is more needed in order to select the next state. Okay, in order to select the next state. And then in a sequential logic, we require the past input history. So in the sequential logic, obviously the sequential logic may contains, for example, the sequential logic, it contains the past outputs, past inputs as well. So the sequential logic requires what? Past input history for deciding the output. So the sequential logic, obviously, in order to, it requires a past input outputs. Okay. So therefore, the FSM, it proves very cooperative in understanding sequential logic rules. So this FSM will make us, this FSM help us to know the next state with the help of the present state and as well as the past or history outputs or inputs. So basically there are two methods for arranging the sequential logic design. So to arrange the sequentially logic design, we have two basic approaches. They are nothing but the Mealy machine and Moore machine. Mealy machine and as well as the Moore machine. So we will see in detail what is this finite state machine. So finite state machine is known as a finite state automation. Finite state automation. So FSM, it is nothing but a calculation model. It's a calculation model and that can be executed. It's a calculation model and can be executed with the help of hardware, otherwise, or software. So the calculations can be observed. Also, the calculations can be made not only with respect to the hardware but also with the software. So with the help of hardware, otherwise software, the calculations can be done, modeled. So this is used for creating what this FSM charts or else finite state machines are help us to create the sequential logic. Okay, so what is the sequential logic? Sequential logic always consists of or it always considers the past inputs. Okay, the history inputs it considers, and then as well as few computer programs. So this is used for creating the sequential logic. FSM will help us to create the sequential logic and as well the few computer programs as well. And then FSMs are used to solve the problems. So the finite state machines help us to solve the problems like mathematics, in games, linguistics, and the artificial intelligence. So FSM finite state machines will make us to solve the problems, critical problems or else the easy problems in different areas like artificial intelligence, which is ruling the world now, and the linguistic and the games and as well in the mathematics as well. In a system where specific inputs can cause specific changes in state, and that can be signified with the help of FSM. So here, if you are considering a system, okay, if you are considering a system, you might see some changes in the output. So these changes in the output can be observed only if there is any changes in the input. So if there is any changes in the input, obviously the output can be changed. So this sort of things you will observe in the FSM, finite state machines. So this is a finite state machine diagram, and this diagram it helps various conditions of a turnstile. So turnstile is nothing but it is a machine where it rotates. Okay, it rotates, it revolves. So whenever placing a coin in a turnstile, this is a turnstile. Okay, it rotates. It rotates upside down. It rotates. So whenever you place a coin over here, turnstile, will unbolt it. Okay, if you place a coin in a turnstile, what it does, it unbolts, it not locks, it unbolts it. And after the turnstile has been pressed, it bolts again. So if you place some coin on a turnstile, what it happens is it unbolts. But after some times, if you press the turnstile, then what happens is the coins will switch onto it. And placing a coin onto a unbolted turnstile. So if you press it, what happens that it bolts again, and placing a coin on an unbolted turnstile. So if you place a coin on unbolted means it's released. If the lock is released, if you place some coin on a turnstile where it is not locked, then otherwise pressing against a bolted turnstile will not alter its state. So if you place some coin on a turnstile and if you are pressing the turnstile, what happens is it will change its states. Okay, it will change its states. But if you place some coin on the turnstile and if you are not pressing it, okay, if you are not pressing it, what happens is it unbolts. It doesn't locks. When it doesn't locks means the state of change is not occurring. The state of change is not occurred. So that is what you can observe here. If you place some coin on this turnstile, what happens? It locks. Okay, when it locks, it pushes. So the coin will go to the next step. Whereas if it is unlocked, okay, if it is unlocked, what happens? It will be in its same position. So that's what we can observe with this example. We can able to know how the states, how the transition of states takes place from one state to the other state. How the outputs are switched on from the one state to the other state, how the outputs are changing, how the inputs, if we give the inputs, how the outputs are changing between the different states. So now we'll see the types of finite state machines. Finite state machines are classified into two main types. They are Mealy state machine and Morris state machine. So coming to Mealy state machines, so when the output depends on current inputs, when the output depends on the current input, then the finite state machine can be named to be a Mealy machine. So one thing you have to remember here in this Mealy machine is when the output depends on the current inputs. The output depends on the current inputs. And then the diagram shows for the Mealy state machine, it consists of two parts, namely combinational logic as well as memory. So this Mealy state machine consists of two blocks, combinational logic and as well as the memory. So the memory in the machine can be used to provide some of the previous outputs of the combinational inputs. So obviously this is a Mealy state machine diagram. It consists of combinational logic and as well as a memory. So this memory consists of the previously inputs, previous or past inputs or outputs. Okay, so based on the current inputs as well as the state, this machine can produce output. So this Mealy machine, it produces the output. The output depends only on the present state of the input. That is what the sentence says. So here the output can be sustained, suitable. The output is suitable only at positive, otherwise negative at the clock signal. So here, as we have the memory element here, we must have the clock signal as well, right? So the output is suitable only at positive. Okay, only at positive level the output is suitable. Otherwise, we get the negative of the clock signal. And then the Mealy machines, state machines diagram is shown. So this is nothing but the mechanism of Mealy state machine. So here if you see, we have A, B, C. We have three states, A, B, C. All the states are circled. The circled is nothing but the states. State A, state B and state C. So here you are observing 0 by 0, 0, 1 by 1, 0 by 1 like that. So after slash 0 by 1, so we are calling it as an input and we call this as the output. Okay, so here basically we have three states A, B, C, and the conversions among these three states are done with respect to the directed lines. So here this is a directed lines. These are the direction lines. That means for the transition of A to B is directed, where here you see we have 1 by 0. That means what? If my input is 1, the output that I'm transitioning to other state is 0. Okay, that's how. So here we see the outputs are denoted by, with 0 by 0. See, 0 by, these are the outputs, 0, 1, 0, 0, 0. These are the outputs. Whereas before the slash, they are called the inputs. So here, 0 by 0, 1 by 0 and 1 by 1. 1 by 1, 0 by 0 and 1 by 0. So these are nothing but the inputs and outputs of that particular state. So sometimes you may see the transition takes place from one state to other state. But some other times we see based on the past inputs or the present input, the state will be within itself. So here we see, for example, state A. So the state A is the transition doesn't take place here, whereas the transition has, or else the state is itself in this own space. So it is 0 by 0. If the input is 0, output is 0. But when I give the input as 1, my output is going as to be 0. So when my output is going out to be 0, that means what the transition of the taking place from A to B. If it is A to B, the output is observed as 0, 1 by 1. If it is the state is in itself in its same position, it is 0 by 0. Okay. And now based on the input values, there are two conversions from every state. So based on the input. So here my input is 0 and my input is 1. So when my input is 0, what happens? The transition is not taking place. When my input is 1, what happens? The transition taking place from A to B. This is with respect to state A. And now we'll come across, now we'll discuss about the state B. So for state B, when my input is 1, the output is 0. That means what? The state B is not taking a transition. But whereas when the input is 0, the output is observed as 0. So when my output is observing as 0, what happens? The state transition is taking place from B to C. Okay, so B to C, the directed line is saying from B to C. And now when my input is 1 and the output is 1, what happens? The state transition is taking place from C to B again back. That means what here? See, when my input is 1, output is 0. And also when my input is 0, output is 1, the transition goes to C to A. So this is how the transitions between the different states based on the input values, present input and past output values can be signified. So this is about the Mealy state machine. So Mealy state machine says output depends only on the present state of the input values. And then coming to the Moore state machines. Moore state machines are nothing but the output depends on current state of FSM. Okay, so here this is combinational logic and we have the memory. So the Moorist consists of two parts, combinational and as well as the memory like the Mealy. They both are one and same, but the output based on the output depends on the present state and output depends on the past state and as well as the present state itself in the Moore. So in this case, the current inputs as well as the current states will decide the next state. So here the present state, the next state is decided only on the present state and the present inputs. Present state and the present input. Based on these two criteria, the next state is been evolved or else the next state is decided. Then depending on the further states, this machine will generate the output. So based on the next state, the outputs will be generated. Okay, based on the next state, the output is generated. And then, so the output of this will be applicable simply after the conversion of the state. So after converting from one state to another state, the outputs are whatever the outputs that are observing, they are applicable. Okay, in Moore machine, after the conversion of from one state to another state, the outputs which are observing are applicable. So see, this is a small example he has given. The Moore state diagram machine shows that similarly A, B, C, D. So here we have 4 states A, B, C, D. Okay, and these are the individual state. The 4 states as well as individual outputs are placed in the circuits. So here these are the states A, B, C, and D, and these are the outputs, individual outputs. These are placed, each states are placed in the circuits. So here these states and the respective outputs, the states and the respective outputs are labeled inside the circuits. In the Moore machine, we will be placing the outputs as well as the states inside the circuits and inside the circuits. Hence, simply the input worth is marked on every conversion. So here you see only input. So if my input is 1 and my output is 0, what happens? The state is not transition, it is itself. And when my input is 1 and my output is 0, so that means what? It is taking transitions from A to B. So so it includes 2 conversions from every state depending on the input value. So this is the input value. If it is 1, output is 0. If it is 0, output is 0. So if the input is 0, it is present in its own state, and if the input is 1, okay, when the input is 1, the transition is taking place to the next state. That means what? The next state is observed only with respect to the past input. Okay, this is the past state, past state input. Okay, and the input and as well as the state. So likewise, the state C. This state C depends only on the past state output and as well as the past state, and D state is observed only on the past states of the inputs and as well as the state. So this is about a difference between the Moore and Mealy. And now we will see applications. Coming to the finite state applications, where it will use. So they are used in games and most recognized by using the artificial intelligence. Okay, as we discussed, SX, even SX also applications of full custom based ASICs. The application goes like in full custom based ASICs. They used in the artificial intelligence and games and as well. So likewise, the 5-state machines also, they give their importance, or they give their priority to utilize in the artificial intelligence. And they also frequent in executions of navigating, parsing text. Okay, parsing text, input handling of the customer, and as well as network protocols. So in the network protocols, input handling, customs, and all these things like FSMs are basically needed. They are used. And 5-state machines are even applicable in vending machines, video games, traffic lights, controllers in CPU, text parsing, analysis of protocol, recognition of speech, language processing. So as I said you, that 5-state machines are they plays a vital role in the back end of the VLSI. So these are the areas where these 5-state machines are maximum used. Okay, so they used in machines, vending machines, video games as well, artificial intelligence and speech processing, recognition of speech, language processing, and etc. And now coming to the advantages. So what are the advantages by using these different machines? Okay, so they are flexible. Okay, they are very flexible and easy to move from a significant abstract to code execution. So they can easily mold, or else they can easily transfigure themselves from the significant abstract. Okay, they can easily transfigure themselves from the abstraction level to a code conversion, or else a code execution, and also low processor overhead, and then easy determination or reachability of a state. So we can easily determine the state of a state in the processing, and also we can easily reach out the next state or the present state with the help of the inputs and as well as the output. And coming to the design, synthesis of synchronous. So how the synthesis can be, or else how the synthesis can be made with the help of the synchronous sequential circuits is the design of a clocked sequential circuit starts to set up a specification and ends with a logic diagram. So here in the sequential circuits, it consists of the memory elements, right? So here it starts with the specifications and it ends with the logic diagram. So here the building blocks, flip-flops, and combinational logic. So the synthesis can be done with respect to the building blocks, flip-flops, and as well as the combinational logic. And here we need to choose the type and number of flip-flops. So how many types of flip-flops and how many number of flip-flops that you are considering in order to synthesize a particular program that is to be needed. And then we need to design combinational logic together with flip-flops to produce the required behavior. So in order to design a combinational logic circuits, we need to be aware of the memory elements and how many types of memory elements and what sort of memory elements that you are considering is to be recognized well, and in order to produce the required behavior of that particular module. And then it's need to combinational circuits. Okay, the combinational part is flip-flop equations, input equations, and output equations. So after recognizing, or else after designing with respect to the memory elements and also the number of elements that you are considering, and then we have to go with the Boolean expressions with respect to the inputs and equations and as well as the output equations. And then design procedure. So in order to synthesize the synchronous sequential circuits, we have a design procedure. So here, to obtain a state diagram from the specifications, what we do is state reduction is if necessary. So for example, in this synthesis process, the designing procedure of the synthesis process goes with the obtaining of a state diagram. So if the state diagram is complex, if your state diagram is complex with different states, many states, what happens if the states are more? If the states are more, the complexity, if you find the complexity in state, one of the advantage, or else one of the mechanism that we can get rid of this complexity is we can reduce the states. So with the help of state reduction technique, we can reduce the state. That is one of the advantages that I can say. And then the second is obtain state table, state assignment. So soon after forming a state diagram, the next state is we have to go with the state table. So out of this diagram, a state table is to be constructed, And then after the state diagram, state assignments. That means with the help of inputs and output, the state transitions between the input and output can be observed clearly and mentioned clearly. So here, obtain state table, state assignment, choose type of flip-flops. Again, here we need to choose the types of flip-flops, D or T, S or what sort of flip-flop that you are considering. So make sure to choose a better flip-flop in order to the transition between the states go smooth. Then use flip-flop excitation table to complete the table. So here, after the state table, we should write the state, after the state diagram, we have to ensure the state table, right? So here, before ensuring the state table, we have to concentrate on the excitation table, and that excitation table can be drawn with the help of the flip-flop that you are considering. If you are considering D flip-flop, the D flip-flop excitation table, it should be drawn. Okay, then derive state equations. So after state diagram, moving on to the state table and then state assignment, and then finally going with the state equations. So after the truth table or as a state table, the final thing is we have to write the expressions. So obtain the flip-flop input equations and the output equations. So the equations with respect to the input and output, Boolean expressions should be written, and then from the expressions, we can make use of the K-maps to function the simplification. So in order to simplify the expressions, we can make use of the Carnot maps. Okay, Carnot maps. And then draw the circuit diagram. So from obtaining, from the expression, Boolean expression, from the Boolean expression, we can draw the diagram, circuit diagram. So this is a procedure which we have to go through when you are synthesizing some synchronous sequential circuits. When you are synthesizing the synchronous sequential circuits, first and foremost thing is you have to collect the states, or else you have to maintain a proper state diagram. The state diagram will consist of the states, the direction lines, and the input and the output. Okay, so if your state diagram is a bit complex, then you can reduce it by omitting the states. So it's nothing but the state reduction process. So after state diagram, you have to go to the state table. Okay, that state table consists of the excitation table. That excitation table is observed with the help of the flip-flops, the memory elements that you are considering. Based on the different flip-flops, different excitation tables can be drawn. And then state assignment. After that, state equations can be observed, and these state equations consist of the Boolean expressions with respect to the flip-flop inputs and as well as the outputs. And finally, from the Boolean expressions, we can able to draw the circuit diagram. So this is all about the synthesis of synchronous sequential circuit. And now we will see the steps of designing procedures. So this is an example that I'm considering. The steps to be followed is, first one is obtaining the state diagram. First and foremost thing is state diagram. So this is a state diagram. It is very important in the design procedure. In the design procedure, first and foremost step is to construct a state diagram. The state diagram consists of different states. So here I have mentioned S0, S1, S2 and S3. So there are 4 states with respect to the input and output, and the direction lines when the transition taking place from one state to the other state. And then example here, here we have an example. Design a circuit that detects a sequence of three consecutive ones. So here 3 consecutive ones in a string of bits coming through an input line. So serial bit stream. In a serial bit stream, we have to see 3 consecutive ones. Okay, now we will see how the 3 consecutive ones takes place. So here state 0, S0, S1, S2 and S3. These are the 4 states with respect to the output mentioned and with respect to the input. So now we will see after state diagram, the next step is we have to write the state table. So the state table assigning the binary codes of the states 0, 0, 0, 1, 1, 0 and 1, 1. So each and every state we have the binary code 0, 0, 0, 1, 1, 0 and 1, 1 for S0, S1, S2, S3. So 0, 0, 0, 1, 1, 0 and 1, 1. And then we choose 2D flip-flop, simplest. So the simplest way, the simplest flip-flop for the execution or the synthesizing purpose that we can consider is D flip-flop. So here we are considering 2 D flip-flops. And then the next state specifies what should be the input of flip-flop. So here the next state, it specifies what should be the input of each flip-flop. So what must be the input of each flip-flop? It will be the next state will be what is that? The next state will specify. So here flip-flop should be the input of each state. So let me tell you. See, this is a state table, right? We are in the step 2 state table. So in the state table, if you observe, present states are A and B. Okay. So how many combinations that we have to consider? 0, 0, 0, 1, 1, 0 and 1, 1, right? So here for present state, input is X, and for next state A and B, output is Y. So if you observe here keenly, my present state inputs are 0, 0, and my present state is, if A it is 0, B it is 0, input is 0 and output is also 0. And then if you observe here, my present state A and B, for the inputs are present state A and B, my input is 1. If my input is 1, what's happening is my output is 0 for the next state 1. When my next state is 1, my output is going to be a 0. Okay, the last one, if you observe, my present states are A and B, 1, 1. So when my A and B are 1 with respect to the input as 1, what happens is my next state, the transition goes with the next state as 1, 1 with the output 1. Okay, with the output 1. And if you observe here, my present states are 1, 1, but my input is 0. When my input is 0, what happens is the transition is going with respect to the output as 1. So if you observe here, after the state table, state equations will be made, right? So based on this state table, state equations are observed with respect to the K-maps. So these are nothing but the K-maps. So using K-maps, the input equations is A of t plus D, that is 3, 5, 7. Why here 3, 5, 7? Here if you observe A, Bx. So A, Bx. So A, Bx, 0, 0, 0, 1, 1, 0 and 1, 1. And if it is 0, 1. So here we are seeing that at this particular state, I've observed the transition of this particular state. That is when A is equals to 0, my 1, 1 is observed at particular M2. And when if it is A is 1, it is observed at 1. So here dA is nothing but AX plus BX. So this is AX plus BX. One is over here and one is over in the B. So likewise dB AX plus B bar X. Okay. So B bar X, why B bar X is here we have complement. 0 is nothing but complement. B bar X, BX. Here it is BX. Here it is BX bar. Okay, so here AX, one is A X plus B bar X. So here it is B bar X. Then the third one is Y is equals to AB. Why Y is equals to AB here? Here it is B bar X bar, B bar X, BX, BX bar. So here it is A bar. So one is with respect to A, another one is with respect to B, isn't it? So it is Y is equals to AB. So from the truth table, from the state table, we could able to make out the state equations. So after the state equations, we can draw the step 4 as circuit diagram. So this is a circuit diagram. This circuit diagram we have drawn with the help of the state expressions AX plus BX, AX, BX bar, Y is equals to AB. So this is Y. Y is nothing but Y is equals to AB. And AX plus B bar X, this is dB, and dA is AX plus BX. Okay. So out of these 3, we can able to make use of this particular diagram. So here, how many flip-flops we have used? We have used 2 flip-flops. Flip-flop 1 and flip-flop 2. So for each flip-flop, the clock is connected. Okay. And here this is the input X. And these are the states A, B bar, B and Y. So this is how the procedure goes for the synthesis of the synchronous sequential circuits. And now we will see with other flip-flop. So here the flip-flop that we have considered is JK flip-flop. Previously we have considered D flip-flop, and now we are considering it with the JK flip-flop. So in designing with D flip-flop, the input equations are observed from the next state. It is simple. And then it is not the case when using JK and D flip-flop. So when you are using the D flip-flop, it is observed that the output equations are observed only with respect, the next state is observed only with respect to the past input. But whereas when you are using the JK flip-flop and D flip-flop, it is not that as easy as the D flip-flop. So here the excitation table, it lists the required inputs that will cause certain transitions. So here these are the characteristics table for the analysis. While excitation tables are used for design So here you observe these are the excitation tables. So in these excitation tables, we are using the flip-flops, JK flip-flops, right, at different time intervals at t, and then t is equals to 1. Okay, and this is for JK flip-flop, and this is for T flip-flop, toggle flip-flop. So for this toggle flip-flop, the timing constraints are Q of T and Q when T is equals to 1. So when T is equals to 1 and when T, the output is observed as 0. When T is equals to 0 and 1, it is observed as 1. And if it is 1 and 0, observe as 1, toggle. And if both are toggle, what happens is it is 0. And obviously for JK flip-flop, we see that when both are 0, we see the J as 0 and one of the output as don't care. Okay, but when any one is the 1, then we see that one of the input, output as 1 and the next is don't care. And if it is 1 0, 1 as K, and if it is 1 and 1, if it is 0, don't care. So the output expressions we got with respect to here is J Q bar plus K bar Q, and here T Q bar plus T bar Q. So this is after the state table, we got the state equations, and after the state equations, this is nothing but the state assignment. So here if you observe present state, input, next state. For the JK flip-flop, input and output. So these are the combinations for 0, 0, 0, 1, 1, 0 and 1, 1. These are the combinations where the next state is observed only with the next state is observed only because of the present state input and the output. Okay, so here if you see we got the expressions as J as BK, BX, K as X bar, JB as X, and KB as A bar plus X bar, and Y is equals to AB. So from these expressions, okay, from this equation, we could able to draw the circuit diagram. This is a circuit diagram based on the expression, and these equations we got it from the Carnot maps, that is state tables. These are the state tables, and this state tables is easy to understand as we are making use of the flip-flop here, JK flip-flop. And for example, if you are considering any toggle flip-flop as well, you can you can make use of the toggle flip-flop here with singles when 0 0 0 1 1 0 and 1 1. In the toggle flip-flop, we observe as when both are 0, it is the don't care conditions. Okay, when any one state is 1, then we observe the output is to be meant as 1. And if both are 1 as well, then the next state will goes, or else the output of that particular toggle state goes as don't care conditions. So here, based on this, if you observe when AB state, the present state both are 1. When the present state both are 1, the next state, if my input is 1 and present state both are 1, then my output goes with 1. Okay, when my output goes with 1, and then when my one of my present state are 1 0, and if my input is 0, and if my input is 0, what happens is my output also goes with 0. Okay, so this is about the equation. From the equation, we can able to draw the circuit diagram, and the circuit diagram, if you observe here, we have X input, and from the X input we have a buffer gate, okay, NOT gate, and we have an AND gate. This is an AND gate, OR gate, this is a NOT gate. So here we have JA, which is equals to BX. So here we are using two JK flip-flops. So this is flip-flop 1 and this is flip-flop 2. So flip-flop 1 and flip-flop 2, we have two outputs with the complement A bar, B bar. So here JA is output input. So what is output for JA? JA output is equals to BX. Okay, so JA is equals to BX, and K is equals to, where is KA? And then K is equals to X bar. K is equals to X bar. See, this is a X bar. KA, X bar. K is equals to X bar. J is equals to BX. So this is a BX. BX, and clock is given to all thing. And then JB is equals to X. Where is JB? JB is equals to X. So simply this is the X. JB is equals to X. And then we have KB. So here KB is equals to A bar. Okay, KB is equals to A bar. So this is a A bar plus X bar. So this is a A bar which is coming over A bar OR gate, right? So plus into X bar. So this is a X bar given to K, isn't it? K bar plus X bar. This is KB, and this is JB. And finally we have Y. So what is this Y? Y is nothing but it is A and B. So Y bar is the AND gate of both A and as well as a B. Okay, output of JK flip flop of JK1 flip flop is A, and the output of JK second flip flop is B. So finally we are getting Y is equals to AB, and these expressions we got it with respect to the this one present state, this is state table. Okay, so state table we got JA is equals to BX. So JA is equals to BX. So here one thing we have to remember is the Carnot maps should be drawn. So the Carnot maps with respect to BX and A, 0 0 0 1 1 0 and 1 1. Here it is 1 and here it is 0. So what we got, J is equals to BX. So here J is equals to BX, somewhere around here. Okay, so JA is equals to BX, and the next Carnot map should be drawn with respect to the expressions that we got. So we got K is equals to X bar. Ka is equals to X bar. Okay, so X, this is AX. So 0 0 0 1 1 0 1 1. It is 0 and it is 1 1 and it is 0. So it is X bar, right? So X bar ante somewhere around here. Okay, we got this from over here, and then what we got, JB is equals to X. So similarly JB is equals to 0 0 0 1 1 0 1 1. JB is equals to X. So this is JB is equals to X. So X is nothing but somewhere around here. Okay, and then finally we got KB is equals to A bar X bar. X bar X A 0 X. Here we can consider AX 0 0 0 1 1 0 1 1. Here it is 1 0 and 1. So here for KB, A bar plus X bar. So here we have A bar and X bar. Okay. So likewise, from the Carnot maps, we can able to write the expressions, and from the expressions, we could able to draw the circuit diagram. So this is about the synthesis of the synchronous sequential circuit. So just remember that in the synchronous sequential circuits, with the help of the memory elements, we could able to store the information, and also in the synchronous sequential machines, we are going with the help of the finite state machines. So this finite state machines consist of the categorization of these final state machines, for the simplification purpose, we are making use of two methods, two categories, that is Mealy and Moore. And in Mealy, the output depends only on the present state of the inputs, whereas in Moore machine, the output depends on the present state and as well as the past states of the input. So here in the synthesis, when it comes to the synthesis process, always remember there are 5 steps to go on. So first step is state diagram. Whatever the state diagram, and if your diagram is complex, then you can have another choice to reduce it by using the state reduction technique, and then go on with the state table and the state assignment. So soon after the state diagram, you have to draw the state table. State table will consist of the present state, input, and next state with respect to the output. So after the state table, the state assignments will be made with respect to the inputs and outputs, and from the state table, we have to write the state equation, and this state equation we obtain by using the Carnot maps. The Carnot maps are also state equation. The state equations is observed with the help of the Carnot maps. The Carnot map simplification of the K maps. Okay, so this K maps are drawn based on the based on the state table. Based on the state table, K maps is drawn, and from the K maps we can easily obtain the Boolean expression equations, state equations, and from the state equations we can easily able to draw the circuit diagram. So this is the design procedure or the synthesis of the synchronous sequential machine. So in the synthesis process, with the help of flip-flops, we can able to synthesize. We have different types of flip-flops, right? The D flip-flop, T flip-flop, JK flip-flop, master slave flip-flop. So among all these 4 flip-flops, any one flip-flop can be considered. Okay, any one flip-flop can be considered, and more than 2 flip-flops can also be used. So here in both the examples, we have considered 2 D flip-flops. Okay, 2 D flip-flops are considered. Likewise, we can make use of JK flip-flops, 2 JK flip-flops, or 2 toggle flip-flops can also be considered, because the sequential machines consist of the memory elements. So each and every flip-flop should be connected with a single clock pulse. Okay, based on the considered with a single clock pulse, and based on the expressions observed, or it's based on the equations that we observed, we can able to easily draw the circuit diagram using the gates. Okay, using the expressions, we can easily draw the circuit diagram. So this is about the synthesis of the synchronous sequential circuits. And thank you.
Like, share and subscribe. Hit the bell icon for more updates.